the main trademarks of this workshop. I'd like to reiterate them, let you know what you're here for, what you're going to gain from it by the end of this. It's hopefully then you don't leave completely empty, but with the ability to put these data structures into work. So we've gone through basics of object-oriented programming, queues and stacks. We've done linked lists. We've done search algorithms. Last time, now we have two left, trees and sorting algorithms. These are arguably the hardest parts of this workshop, the hardest topics I chose for this, but we'll get through it together and with time. We'll take our time with it. So each session is recorded. Each session will be an hour or and a half long. I plan to make it an hour long, the explanation itself. And I'll be writing most of the code on the board because I find it more engaging that way. So the general routine, don't feel embarrassed to ask questions. Asking questions ends up benefiting everyone. Please keep the discussion centered around the current workshop topic as well so that I can stay within the margins, the time margins that we set initially. Okay, and the workshop goal, what I promise you should be able to do by the end of this. By the end of this workshop, you'll have a strong foundation in both object-oriented programming and data structures and algorithms, which will be useful in all blocks of programming. AI, software engineering, cloud computing. Whenever you're working with code, you'll most likely come across some way or some manipulation of data structures and algorithms, how to make them efficient. Table of contents, each session follows the same structure. We have the key concepts. We'll go over general trees versus binary trees. We'll be going over real-world examples. We'll have some exercises and a code demo to see how this is implemented in Python. I want to dive back to a previous data structure that we learned before. Maybe I'll move this a bit to the side so that I can go further back. Okay, so let me push this backwards. All right, so does anyone, I won't ask too many questions, but for just reference, does anyone remember linked lists? Can you give me just your definition of a linked list? How would you define it? Just put it into words. It doesn't have to be any like in-depth definition. Just based on what you saw of linked list, what is it? If you understand how lists work in Python, they have lists, which are just linear sequences of data within Python. Yeah, so big O notation is what we use to measure the efficiency of the algorithm, how fast or how quickly, how the rate at which the time for the algorithm changes based on whatever variable. And we have lists, which are just blocks of contiguous data within our memory when we run a list in Python. So say let's call this a regular list equals that. We can have data, any data at all, not just numbers. But yeah, and the thing about lists is that they're contiguous. So we're able to determine the position for each of the data elements because they're in one block. So if I wanted to figure out what number is on position 3, so these are the positions 0, 1, 2, 3, 4. I can just say, give me the list at position or index. We call them indexes, computer science, index 3, and that should give me. Yeah, no, that should give me. Yeah, I got the. Should be 1, 2, 3, and that should give me 4 exactly. That equals 4. And linked lists are a little different from this because instead of having one contiguous block of memory in our computer, we have these nodes. A linked list is node based. We have these nodes that we create in the data to essentially replace what we have in terms of positions for the data. Now we have nodes that contain each data element. So a node can have the data, in this case 1, and then an address as well, and address. And these nodes are then linked by their addresses to each succeeding node. No, the data itself, you can have the data be anything. I shouldn't have numbered them. I should have just done random data. Yeah, I showed you the Python tutor, which lets you visualize each step of it. It's super useful. Like whenever you just to keep in mind, whenever you come across like an algorithm you don't understand, put it through like some debugger like Python tutor, so you can see each individual step. It's so helpful. And try to understand like the way they're visualizing it, what each thing's supposed to represent. The more you do it, the more it'll just become super easy to just decipher like any algorithm that may seem complicated. And it's very helpful. I can't stress that enough. And when we link these, you have a linked collection of data, but they're not contiguous. They're not next to each other. That's the main difference. They're not we can't index into them because they're just random pieces of data scattered across the memory that are just linked to one another by some address. That's the main distinction. This is what we refer to as node-based data types. And what time complexity do you remember we said that linked lists have? Yeah, the binary search, binary search, yeah, linear and binary search. Linear search has what type of time complexity? Takes more time because we're just doing each step for linearly. Exactly. And that's why we say for linear search, because we go through each individual step. I'll just highlight all the time complexities that we went over. We went over logarithmic time. So we have logarithmic time, log of n, O log of n, O of n, O of n quadratic time, um, O of constant time, and also O of linear logarithmic time. So these are the time complexities that we went over. So we have logarithmic, linear, quadratic, constant, and linear logarithmic. And O of n would be linear time, which is what linear search would have. So because so we have n here and we have the relative time, rel time here. With each additional element that we have, the time complexity also increases an equal amount. Just so if we have 5 elements, the time complexity is going to be 5 in whatever relative time unit we use. And for logarithmic time, it grows like this. So with every new element, that's a logarithmic time. So this one, logarithmic time. And what do you remember about logs? Let's briefly just go over them. So if you have log base 2, 8, this would be n. Let's say we had 8 elements in this. Exactly. So if we have 8 elements, the relative time complexity we're going to have is going to be 3. By the time we reach 8 here, it's only going to be 3 here. So that's the power of understanding time complexities. So all of this is to come back to our linked list data structure. And I should have, when I asked for a time complexity, I should have been more specific. Um, Instead of just the time complexity of a linked list, let's talk about the actual operation. If we want to, for example, to remove an element um, from the start or the back of a list, what Python's going to have to do in the memory is it's going to have to copy all the elements and then find a new block of data to associate those elements with, and then add the element to the front. O of n. because we're taking each individual element, we're copying it. We have to traverse it first, copy it, and then put it into a new array with the new element that we're adding. Say we were adding like a 0 to the front. We'd have to take all the elements, get a new array, and copy and put all the elements in that array with 0 in the front. We couldn't just push it to the front. Behind the scenes, it may look like that in Python, but like behind the scenes, what Python's doing is it's internally just associating a new amount of memory to this block. And the memory for this new block isn't necessarily going to be 5, isn't necessarily going to be enough for the new element. It may just double the existing block so that it can compensate for maybe 8 elements instead. Every time you add something and there's not enough capacity in it, Python's going to look at that and double it. Just going to assume, hey, you need more space? Let's just double it. You don't need to tell me how much you need. I'll double it. You have 50 spaces, but you need 51. Let me give you 100, basically. And that's linear time complexity that we have there. But for linked lists, whenever we want to change or add an element to the front, we don't need to copy all the elements because they're not even inside of a contiguous block of memory to begin with. They're just individual nodes throughout the data. So we don't need to push or copy all the elements and put them in a new block. All we need to do is just make some node somewhere in the memory. This is data, a new node. Let's call it new, or give it the data of new and the address. And all we have to do is take the address of this new node and set it to the previous front node. So we just have like a bunch of blocks and we just rearrange them essentially. We just added a new block and just put it to the middle, to the front. And yeah, so that was a brief review on linked lists. The reason why I reviewed this was because linked lists are very similar to trees, which is what we're going to discuss. Let's define what a tree is. Let's take a step back and just define what a tree is. So first of all, we had our linked list. I'll just give you a definition for that, and then I'll give you a definition for tree. So a linked list, what we just talked about, let's go to definition. Linked list is an abstract data type where or which is it contiguous or non-contiguous? Contiguous just means touching. Not contiguous because all the elements are just random blocks in the memory that we just kind of link. We don't put them in a little box and group them. So it's non-contiguous. But it is sequential. Sequential. Because we iterated from front to back. We go in a linear direction, basically. Sequential and is non-contiguous, is sequential, and is node-based, okay? Node-based. Node. So let me rewrite it. So it's node-based. It's a node-based, non-contiguous, sequential data type. So that's the formal definition. It's not necessary. I wouldn't say like it's good to think of it as something to understand, but in case someone's like, or an exam question, what is a linked list? If you give this answer, it'll be correct. So we already know this. This is something we've already reviewed. Now let's talk about trees. So then what is a tree actually? So what a tree is Yeah, that's the general idea. I mean, most of these data types, their name implies kind of what their functionality is. And with a general tree, like you said, it branches out from a single root. Um, so let me just give you a definition. So a tree is also an abstract data type which is node based and hierarchical. Hierarchical. So there's a hierarchy between each element. So it's which is yeah, I said node based, node based. So just like we had these nodes in linked lists that were just kind of linked linearly. I mean, this doesn't look linearly, but they're following a consistent path. Yeah, these nodes, shape doesn't matter, just a container. In where they followed a linear path. For trees, it's different. Let me get a bit more space so that I can draw this fully. Trees, we have one root node. This is what we call the root, the first thing, the first node. In linked list, it was just an arbitrary node at the front. That's what we determined where it started from. For trees, it starts at the root and branches downwards. So let's call this the root. And then I have three links to three other nodes. So already you were noticing a difference between the linked list and the trees. The linked list was already always a single link to a next node. But now we have a root node at the start, and any number, this could be any number. I'm just choosing three because I don't want to dwell on that too much, but we have a root node with an unspecified, that a node that can have an unspecified amount of links. So the relationship between and then these nodes connected to the root node, we refer to as child nodes. Child nodes. Okay? They're child nodes to the root node. So you have to, so saying that they're child nodes is an incomplete sentence. They're children to this root node. Because the reason why we say that is because these child nodes can have their own children as well. And these become child nodes. It can go on forever, basically. And these child nodes are parents to these child nodes, but they're still children to the root node. Every time we have this a new relationship between children and parent nodes, we call these subtrees. So we have the main tree, which is the root until the bottom. And then we have within the main tree, you have subtrees with their own children. So this would be considered one subtree. Okay. And so let me just redraw. So we have a root, and you're asking if let me give this one three children. Okay. Since this is a subtree, right? This is a subtree as well. Um, and this is a subtree because we have a relationship between a parent and a child node here. So I think you're asking is if we had another level down, for example, this, would it also be a subtree? The answer is yes. This is also a subtree because there's a relationship between a parent and a child node, one or more child nodes. So, and it can keep on going forever as long as the hierarchy goes down, right? Um, but once we reach the point where the children don't have their own children anymore, that's what we consider the I forget what the terminology is, but we can just refer to it as the bottom of the tree, right? I think I think it's just the bottom of the tree. Yeah, the height is considered the nodes that you traverse until you reach the bottom, and the bottom is once you've reached the nodes, the final subtree with no children. And these nodes here, they're not called parents, They can't be called parents because they don't have any children. So we refer to them as leaves. We refer to them as just leaves, leaf nodes, because they don't have any children. They're the bottom of that subtree, and this would also be considered a leaf. It doesn't have any children. It may be higher up than these nodes, but it's still a leaf. It doesn't have any children. That this subtree has reached its end, and here this subtree reached its end as well, and so on. Yeah. So what we defined here is a specific type of tree. This is the most common type of tree, just a general tree. All right, a general tree. It doesn't have any real it has the least amount of restrictions out of all the trees. There's many different types. We're only gonna go over the two main types, which is the general tree and the other one. So this is a general tree. Um, and one thing to remember about the general tree, each node could have any number of children. Could have hundreds, could have thousands of children. There's no limitation there. So just remember that as we're going into the next tree. Yeah. So we talked about general trees. Um, what do you think is the difference? What do you think a binary search tree is? We have a general tree. What's a binary? You can look at the definition and yeah. No, that's a good definition. So let's flesh that out a bit more. So we said a general subtree is an abstract data type uh, that which is node based and hierarchical. A binary search tree. Let's get a definition for that. I'll call it BST. Binary search tree is also a node based data type, which is hierarchical. Hierarchical. Okay, so the same as a general tree. No differences so far. But, big but, each node in the BST can have a max of 2 children. Okay? A max of 2 children, which is what you said, which is correct. So that's one condition, a max of 2 children. There's another condition on top of this. So a max of 2 children. Do you have any idea what the second condition is that you saw? Exactly, exactly. So what does that mean? So we know that we're talking about data structures, right? We're talking about data types. The purpose of a data type is to store data. And this data can be numerical. It can be um, a string of characters. So when we're discussing data types, um, let's consider the fact that we're using numericals. We're using integers, just numbers. Let's say we actually store a value in this node that we had before. So give me a random number. 5. Okay, 5. This is a binary search tree. So how many child nodes could it have? This is the root, so 2. Have a maximum of 2. Give me another number to enter into this tree. 6 and 9. So where would 6 go? Which of these two nodes do you think 6 would go into? Just put 6 on the right side. So just stop there. Okay. So we've put 6 on the right side, but now we still have 9. And the reason you put 6 on the right side is because for a binary subtree, all the uh, all the nodes on the right side of the root or the parent have to be bigger than the parent, and on the left side, all the nodes have to be smaller than the parent. Right? That's why we put 6 on the right side of 5 of the root that has 5. But now, what do we do? Since we already have a value in the right node. Where do we go from there? What could we do? Do we put 9 here because we have no space for on the right side for 9 because 6 is taking its place? What we do is because 5 already has a node, we start from the root from 5. We see, oh, there's a value on this node. Let me just make a new node. Let me just make 2 new node possibilities. So there's nodes here now. And the reason why I put 9 on the right side is because 9 is bigger than the root and 5. But we checked to see we can't put it on the right side on the direct right node because it's already occupied. We go there, we look at 6, and we see it's also bigger than 6. So which of these nodes would 9 go into? Like on the right side. On the right side of, let's try adding another value. Yeah, let's say we have four. Let me make this 7. Okay. Let's say we want to insert 6 again. On the left side. 6 on the left side. We always start from the top when we're inserting. Okay, so we have to add a number which is smaller than 5. Well, but the only number we don't have the luxury of choosing. We can't choose. I've given you 6. Put it in my tree. So, it will be start from the 7. Whenever we're inserting a value. If you already have like a tree with a bunch of subtrees, you always start from the root. We always start from the root. We can't decide we want to insert from like somewhere at the bottom of the tree. We always start from the top and the root of the tree. So we've gone down and we've seen we have 7. Yeah. So we like 6 is lesser than 7. So we can write 6 on the left side of it. Exactly. And that's how it goes. Anytime you insert a new value, you always have to compare that new value to each node that you end up traversing before you eventually reach the point where, okay, I've reached this point, I've reached the end. Let's see, is it bigger or less than? If it's bigger, to the right. If it's less than, to the left. Okay, let's try one more. 3. I want to put 3 in here. 3 will be on the left side of 5. Okay, so we start here, we go here, it's empty. All right. And yeah. And that's the gist of binary search trees. And the reason why we do this is the reason why we go through all this trouble to have a completely different tree is because we're essentially creating an environment where we can easily search for data. Does this data structure, binary search tree, remind you of another data structure? Let's try with an example. We'll just have a bunch of numbers, and then we'll insert them into a tree, and then we'll compare how quickly we can find a number here versus in the tree. So give me some random number. Let's put these into a binary search tree. So for inserting, whenever you're inserting data into it, you would start from the front. So you would take the first element first and make that the, what do we call the first element of the binary search tree? The root. So 6 is going to be the root. We have to insert 72 first. So where do we insert it? The right side, 72. Right side of 72. Okay, so you traverse from 6 down to 72. 105. Next. Left side of 72, so 6. So it's bigger than 6. Go down to 72. Smaller than 72. 52. And 69 will be on the 64. 64 will be on the left side of 52. Like right side of 52. Okay, so you started from here, went down, saw it's bigger than 6, smaller than 72, bigger than 52. Goes down here. Okay. Then right side of 64 is 77. Okay, 6, bigger than 6, smaller than 72, bigger than 52, bigger than 64, 77. Yeah, and So 6, bigger than 6, smaller than 72, smaller than 52. Get a left node for 52. So bigger than 6, smaller than 72, smaller than 52, bigger than 24 goes here. All right. So say I wanted to find the value 24 in a list. I'll just do the list one. I would use a for loop and tell it for all the elements in this list. So let's call this numbers, num. I'll do a Python algorithm like for num, for n, or for number. Let's call this num list. In num list. Then I have a condition if number equals 24, yeah, 24, return true. It's going to do a bunch of iterations. So it's going to start by looking, num is going to first equal 6. So this is the first iteration, iteration 1. I'm going to check to see if 72 is the number. It's not. I'm going to do another iteration. I'm going to do another iteration. 4, 5, 6, sixth iteration. 7th iteration. Okay. So we found 24 after 7 iterations in this loop. So how Python would have gone through it. Now, say we wanted to find 24 in this binary search tree. Where would we start? From 6. We start from 6. So we start from 6. Our target is 24. So what would we do? Do you remember something from the binary search algorithm? Yeah, but that was for like the search algorithm in a list. Now we've completely changed. We've put ourselves in an environment perfect for binary search. We don't need to go into some middle because if you notice, we've kind of put 6. 6 is already kind of in the middle here, right? It has values on the right side that are bigger than and values on the left side. So we've already kind of put it in the middle. Yeah, but say what if we had what if we had one here? How would we tell it to go to 72 and not to this node? It's comparing, just like we did in binary search. We compared the middle to the target we want, saw which one is bigger. So we're comparing here as well. We're comparing this target. We want to find 24 to 6. We've seen it's bigger. We know that all our bigger nodes are on the right side, so we can only look on the right. All right, so find 72, and I'll look at that. Yeah, we've told the algorithm all the values lesser than are going to be on the left side. So if your number is smaller than this, it's definitely going to be on the left side. So this is our first iteration, second iteration. Exactly. Now our third iteration. Notice a difference here? Notice a similarity here between a binary search? 3 iterations. And we have how many elements? We have let's erase this for now. We have 1, 2, 3, 4, 5, 6, 7, 8. So let's try logarithmic time. What do we say log base 2 of 8 equals to? Equals to 3. We have 3 iterations. In linked lists, there's just one type of traversal, just linear from front to back. In binary search trees, we have 3 types of traversal. Okay? So let's craft our tree from before. In linked list, yeah, you're kind of traveling through the links of each node. But the point of traversal, the thing that has to occur is you have to visit each node at least once. It has to be confirmation. I've been to every single node at least one time. For linked lists, for linear data types, it's simple. We just go from the start, we just go forward. But for trees, it's a bit different because they're hierarchical. There's no just linear path, just follow. So we have 3 traversal methods. The first one is in order traversal. And let me write it down. So can you see it all right? The in order traversal. All right. So we have in order traversal. And this traversal methods tells us that we have to start from the left, go to the roots, and go to the right. Okay? So we start from the left, go to the roots, and at the right. So left, it's in order. I mean, as you notice, we're starting from the left in order. We're going to the right or to the roots, and then we're going down to the right. So left, roots, and then right. All right. So let's just try and perform this traversal on this tree that we've made.
9, 432.
Yes, that's where you can come into the trouble because you have subtrees, right? And how do you decide whether or not, oh yeah, you've already done this left subtree? How do you decide, oh yeah, I've come across a new subtree when I was going to the right? Do I go
Maybe
back
we
and
have
go to the root again?
to finish left first.
Yeah, I will go to the left. But like when you're doing the traversal, like imagine you have a really complex tree. It becomes really just tedious trying to figure out, oh wait, I'm starting from the left, I'm going to the right. There's a new subtree, and there's something on the left side. I'm going to go to the left again, but now my order is all out of whack. I don't know if I have to go back to the roots and start again to the right. So there's a method that you can use that I found very useful. So whenever you have something like this, for in order traversal, try drawing it. Try writing it down. So if you already have it written down. So to start the traversal, I'll draw a line here, and I'll say this is my first contact. I've made the first contact with the root. I set up a rule for myself. I need to make two contacts on each node before I register it. Okay, before I register it, I have to contact it twice before I register it. Each node I have to touch twice, at least twice before it's registered, and I can move on to printing the next node. Okay, so this is my output. This is where I'll print it in this box, right? So I'll start here, made my first contact, and then I'll go down to the left. I've made another contact here. I'll go down to my 5. I made a first contact on 5. Go down to my 6. I've made a first contact on 6. There's no further leaf node. So, you know, let's just imagine I have these little empty branches with no data. I'll make a second contact around this left branch for this node. That's my second contact. My rule: two contacts before I print. I've made two contacts on 6. I can print 6. This is the first thing I printed out. And if I had a node here, I would make a third contact. But it doesn't matter for now. For in order traversal, two contacts, and then I can register it. Okay? So let's imagine.
More than two will be possible. More than two will be possible and it's okay. But less than two will be not okay.
For in order traversal, I've made the rule that it has to be two, at least two.
Yes, yes.
We're going to be making 3 in total every time, no matter what. But for the order in which I'm going to print this is the first node to get two contacts is the first node I'm going to print. The next node to get two contacts comes next. So when I go up here, I've made a second contact on 5.
Yeah,
right?
what about the children of 6?
The children of 6, 6 doesn't have any children. They're just empty branches. I just kind of drew little branches just to show how, because like every time I'm traversing, like if 6, 7 didn't have a node here, I would have just done this. All right. It's just to show you how I'm traversing the tree to help you visualize it better. But the 6 is a leaf node. It's leaf node with just imagine little empty branches, little twigs on it. Now I've made a second contact on 5. So we're already kind of true to the in order traversal. We started from the leftmost tree, leftmost node, which was 6, and now we're moving on to 5. But we're doing it in such a way that it's easy. It's not like we don't have to kind of try to determine whether or not we're actually doing it in order. We're just following this rule. 2 contacts before I'm going to register you, right? So we go up to 5. In addition to this branch here, this left branch, it doesn't look like it's on the left, but it's on the left. No, oh no, sorry, it's on the. Oh no, no, I made a mistake. I made a mistake. I'm sorry about that. I made a big mistake. It's on the right side.
It's on the right side.
Yeah,
Like we can write 4 also in it.
yeah,
It will be more easy to understand.
yeah, but we don't need to. We can just have like a little empty branch here. All right. So let's erase this for now.
Can we make 4?
Hmm?
Can we make 4?
You're gonna make 4?
Yes.
That's okay. Yeah, sure. So we have 4 here. Okay. So let's backtrack to this node here, to 5. We go down, and we've made a first contact on 4. We go down. 4 has little empty branches. Make a second contact around the left branch. So we print 4 because we've made 2 contacts. Make a third contact around the right branch for 4. Nothing happens. We go back up. We've made our second contact on 5.
Now what we do? We go to the 6 or the 5 is.
Before we do that, we have to register 5.
Yeah. Oh, okay.
Register 5. Yeah, just like we were registering both of, like, we had a third contact after we registered this empty branch. This branch just happens to have something on it. So we're going to go down, make first contact on 6. 6 has little empty branches. We're going to make a second contact on 6. And we register 6. Make a third contact around this empty branch. Nothing happens. We go back up, make our third contact on 5. Nothing happens. We go back up, make our second contact on 7. We've made it back up to 7. Register 7. Go back up. We're back at the roots. Now we can print the roots. Print the roots. And now we go down the right side of the roots. We've done our left. Now we're on the right. But the rule still applies. Still, every single node has to be visited twice. Yeah, because it's its own subtree. It wouldn't become the roots. The root is always the first node, but it has its own subtree. So in the context, it's the root of this subtree, I guess you could say. But the root is always the first one. So we've made our first contact on 16 now. We go down to 9. 9 has little branches. Make our second contact on 9. We print 9. Make our third contact. Doesn't matter. We were just moving forward. Now we make our second contact on 16. There we go. Now we go down. We visit 32 with little empty branches. First contact. Second contact. Register. Third contact. Then go back up. Third contact on 16. Third contact on 8. And we've done our traversal through this process. So anytime you're trying to do in order traversal to get the values inside, to traverse the values in some tree that you've made, use this method. Just remember 2 contacts for in order traversal. We have in order traversal, which is left, root, right. Left, root, right. Now we have the other 2. So we have pre-order traversal. Pre-order traversal. Let me write that here. We have pre-order traversal. And pre-order traversal, if uh, if in-order traversal is left, right, left to root, right, what do you think pre-order traversal would be?
It's like root, then left subtree, then right subtree.
Mm-hmm. Exactly. Root, left, and then right. It's okay if you look there. Um, I just want you to tell me, basically. So it's root,
Okay.
left, and then right. Okay? Root, left, and then right. So what's the first thing that's going to be printed?
8.
8. Every single time we want to do pre-order traversal, the first thing, using this contacts method, how many contacts before we print something?
1.
One? Yeah. And that makes sense, right? Because we always start from the roots. That's the thing. We always start from the roots, doing anything. We always start at the roots.
So we don't need to do second interaction.
Don't need to do second interaction. I mean, we still do it, but we only need one before we register because the moment we touch the root, it's already there. It's the first thing. Root, left, right. So start from the roots, and on our first contact, we let me erase this one. We have a new rule. Now, rule is that on every first contact, register data. First contact, register the data. Okay? All right. So, first thing we print, like you said, is going to be 8. Next, what do we do?
Left side, so 7,
We go down to 7, make our first contact, print 7.
then 5,
Next contact is going to be 5, we print 5.
4,
Next contact is going to be 4, we print 4.
then
Now we have yeah, 6, but before this, how do we reach 6?
5 from 5.
From 5, we're on 4. So
But
are you saying we go back?
yeah,
But before we go back, what do we do?
we
We,
do we again do a second interaction.
yeah, because whenever you reach the end, you have to kind of circle back. So you have to do the other interactions, even if it doesn't matter, regardless, even if it doesn't affect whether or not we're printing, still do them because it helps to keep you consistent, keeps you on track. So we just imagine we still have our little branches. So we make our second, third interaction, and then we go back up, second interaction of 5, nothing happens, we've already printed it. We go down, make our first interaction with 6, we print. And then second interaction, third interaction with 5, then third interaction 7, third interaction with 8. We've already printed all these. Everything's done on this side. 7 should have had, should have been this, because 7 doesn't have any right branch. It has a little empty right branch. But where do we go from here? We have 8, 7, 5, 4, 6. It doesn't really look in order, right? Looks pretty random.
Yes, then 16, then 19. Yes,
16,
then 19.
first interaction, we print it. 9, that's, yeah, it's 9. Print it. Second, third, around the empty leaf. This is our second interaction with 16. And go down, make our first interaction with 32. Then go around 32's little empty leaves. Go back to 16, third interaction. Go back to 8, final and third interaction with the roots. All right. So this is our pre-order traversal. That's how we do it.
Not written anything about the two interactions.
Just based off of me using it for a while and just seeing how a bunch of other people do it. It's a convention. I don't know how widespread it is, but it's a very useful way to do it. Very useful method if you know it. It's much more useful than in an exam, for example, they tell you in order to traversal go. And during the stress, unless you have like a method like this, if you have a method like this, you can do it really quickly. But otherwise, you're kind of guessing at some points. I'm gonna do the last one really quickly because I think you already get the idea for traversals. You want to already make a guess for what method, what condition we're gonna put for a post order traversal. Or actually, no. Before you do that, if in order is left, root, right, pre-order is root, left, right. What's post order? Left, right, and root. Exactly. So what do you think the rule is that we're going to enforce? We had two contacts for in order. We had one contact for pre-order. So what do we do for post order? Three. I mean, it's really the only option because we do a maximum of three anyways. We don't do any more than three for any node. We always only visit them at most three times. So yeah, three. The thing that you'll notice is that the for all the traversals we always start the right. We never do right first, basically. We never do right first. But notice how through all the traversals, the right is never the first thing we do. It's always either the second to last or last thing that we do. So we have left, and then we have right, then we have root. Cool. And instead of for one contact, we're going to make three contacts. And let me erase this thing. So first contact on 8. Do we print? No. Yeah, it's gonna end up starting at 4 because that's the first third interaction we're gonna end up having. So let's speed through that. So first, second, third. So we're at 4. Then we go up second. Can you see like the number that I'm on? Not like the whether I'm first, second, or third. So first interaction, second interaction, then third interaction with 6. And then the third interaction with 5. So we print. Okay. So then the second interaction with 7, then the lead, and the third interaction with 7. So we print. Second interaction with 8. We don't do anything. We go down. 15, first interaction, then 9, first interaction, then a lead, second and third. Reprint. Second interaction with 16, then 32, first interaction, then leave is second interaction with 32, then third interaction with 32. Reprint. And then 16 with third interaction. Reprint. And 8 with third interaction. Last and final one. There we go. We have these operations. Traversal is something that you have to keep in mind because there are multiple ways to traverse a binary search tree. Let's go into a real world application. So we've talked a bunch of theory on what this concept is and how it works. Let's actually very briefly. I'm not gonna have a whole I'm not gonna spend too much time on it because we need to get to the code demo eventually. One of the ways that we use trees in like actual computers and actual software is through file systems. So are you familiar with file systems? Comes to mind like computer file systems. So you have in your computer you have the library button, this app. Then you click it, and then it shows you all your apps in the computer. And then within the computer, you have a folder. You have one folder. Maybe this folder is like a documents. You have a documents folder. Oh, okay. Like the different type of files, like .py is for yeah, that's one file. Is for documents. Yeah, exactly. And they have to be stored somehow, right? Yeah. And you store the files within folders. So in this case, the folders that you store the files in would be parents.
Okay. Yes.
All right,
Yes.
parents. Within these, within the documents, you may have a bunch of other folders inside of this documents folder.
It's subtree.
Yeah, and that's the subtree.
As a subtree.
Yeah. You
Yeah.
may have one folder for, I don't know, like pictures. This is not how it's in the computer, but like let's just say another folder for pictures, a folder for videos, and then you just have then just some random PNG file, some random picture just in the documents. You could have put it in the pictures, but you just left it in at the same level as documents. Uh, and the file, because you can't put anything inside it or expand to another directory, it's just going to be a leaf. So in file systems, the folders are the parents, can be parents, and the files are just that's the actual app. You click on it and you open it. You don't go into some other uh, branch of networks. So let's just say this is just a random picture, random dot png. All right, you click it and it opens a picture. That's the end. That's the end of your traversal. You've come to a picture. But for pictures, you can go into pictures, and then you can have a lot of pictures. This is a little bit not a great way of drawing it because I kind of went into it, but just imagine. So within pictures, you'll have your own directors on videos. You have your own, and it goes on like that. That's how file systems are used in computer. You notice that trees are a very common data structure, and you'll see it. I think you'll most likely see it in like if an interviewer for a software company decides to test you on data structures. Not I feel like 9 times out of 10 you're going to encounter some trees. It's a reverse a binary search tree or something like that. It's I think it's the most common. It's also my favorite because I just find it one of the more interesting data structures. So yeah, so it's an important data structure to understand because usually a lot of people just they brush it off because they don't understand it, they can't figure it out. But invest the time in understanding it, and it'll become a very useful asset.